The earliest computed tomography systems, like this 1971 EMI brain scanner, were monumental achievements, but they required massive, bulky physical hardware to process even the simplest cross-sectional images. Today, clinical CT scanners are sleek, incredibly fast machines capable of mapping human anatomy in fractions of a second. But if you strip away the plastic casing of the gantry, the internal architecture relies on three critical nodes: the X-ray tube, the collimator and filter assembly, and the detector array. To produce high-resolution diagnostic images, this system must perfectly optimize a polychromatic X-ray beam, capture nearly every photon that passes through the patient, and physically rotate the entire assembly fast enough to freeze biological motion. Mastering CT physics means understanding both of these systems, how static hardware shapes the beam, and how the mechanical gantry evolved to reach its modern speed. This diagram shows an unrefined X-ray beam emerging from the focal spot. The raw beam is polychromatic, meaning it contains a chaotic mixture of both high and low energy photons. Before reaching the patient, the beam passes through a filter. This barrier absorbs the low energy, or soft X-rays. Because soft X-rays lack the energy to pass completely through human tissue, they only increase the patient's radiation dose without ever reaching the detector. By stripping away those lower energies, the filter artificially narrows the spectrum, creating a more uniform, monochromatic beam. The mathematical algorithms that reconstruct CT images rely entirely on this assumption of a single energy beam to calculate tissue density accurately. However, human bodies present an anatomical challenge. A torso is roughly oval. The lateral edges are much thinner than the dense center, which means X-rays passing through the sides experience significantly less attenuation. This animated diagram demonstrates the hardware solution, the bow tie filter. By using a shape that is thicker at its lateral edges and thinner in the middle, the filter precisely compensates for the patient's anatomy, equalizing the overall attenuation profile across the entire beam. Next, a collimator is placed between the filter and the patient. This component physically clips the edges of the beam to restrict scatter radiation from exposing tissue outside the desired slice. Every piece of this beam-shaping hardware serves a single purpose: to remove non-diagnostic photons before they ever hit the patient, strictly minimizing the radiation dose while standardizing the mathematical data the system will receive. Once the beam passes through the patient, it strikes the multi-slice detector array. Modern scanners utilize immense grids for this task, typically housing 8 to 64 rows, with 1,000 to 2,000 individual detectors tightly packed into each row. Early CT systems relied on designs like the one shown in the schematic, an ionization chamber detector. This was a single vessel filled with krypton or xenon gas, partitioned by thin tungsten septae. When X-rays entered the chamber, they ionized the gas to produce a signal. But this design had a critical flaw: a detection efficiency of roughly 50%. Half of the diagnostic photons passed completely through the gas without interacting, making these chambers entirely unsuitable for modern multi-slice scanning. The current clinical standard, shown in this cross-section diagram, is the solid-state detector, or SSD. It operates using two distinct material layers to capture the signal. In the first phase, incoming X-rays strike the top, solid scintillator layer. This material immediately absorbs the radiation and converts the X-ray energy into flashes of visible light. Directly beneath that is the photodiode layer. It captures those light photons and translates them into a stable electrical signal that the computer can process. The SSD provides three major operational advantages: an exceptional 90% detection efficiency, extremely narrow gaps between active elements for high geometrical efficiency, and a tiny physical footprint. If multi-slice imaging still operated at a 50% capture rate, the required radiation exposure to achieve a high-resolution scan would be prohibitively dangerous. The 90% efficiency of solid-state detectors is the core reason modern CT is clinically viable. Even with high-efficiency detectors capturing photons, a complete diagnostic image requires mapping those photons from every perspective. This necessitates rotating the entire hardware assembly, both the X-ray tube and the detector array, rapidly around the patient to collect data from hundreds of angles. This diagram illustrates the mechanical baseline of the very first generation of CT scanners. The architecture consisted of a single X-ray source aiming a pencil-thin beam directly at a single opposing detector. To capture a full slice, the machine utilized a translate-rotate motion. The tube and detector would translate linearly across the patient, stop, physically rotate 1 degree, and then translate back across. Because of this mechanical stop-and-go process, a first-generation scanner required 5 full minutes just to acquire a single slice of data. This diagram shows the second-generation upgrade. By expanding that single detector into a small curved array of up to 30 blocks, the system could capture more angles during each linear pass. This hardware update dropped scan times down to between 5 and 90 seconds per slice. However, the requirement to physically translate the heavy assembly back and forth remained a hard mechanical bottleneck. As long as the gantry had to stop and slide, the physical speed limit of the hardware made it impossible to completely freeze the natural motion of a breathing lung or a beating heart. The engineering breakthrough that eliminated this bottleneck was the slip ring. By using conductive brushes sliding against stationary rings to transfer power and data, engineers eliminated the need for heavy, tangled power cables, allowing the gantry to rotate endlessly in one direction. The addition of the slip ring enabled the third-generation scanner, which we see in this diagram. This is the undisputed clinical standard used in hospitals today. It operates on a rotate-rotate geometry. Because the X-ray fan beam is broad enough to cover the entire anatomical slice at once, the tube and the massive detector array rotate together continuously in a smooth, uninterrupted circle. The linear translation step is completely gone. With the translation bottleneck removed, a modern third-generation system can spin fast enough to acquire a full slice in roughly 0.3 seconds. Engineers also briefly developed fourth-generation rotate-fixed systems, where only the X-ray tube rotates inside a complete stationary 360-degree ring of detectors, though these are less common today. For the absolute limits of speed, this diagram shows the fifth-generation electron beam scanner. Designed specifically for cardiac imaging, it contains 0 moving parts. Instead, an electromagnetic field rapidly deflects a beam of electrons across a static tungsten target ring situated beneath the patient. By replacing mechanical rotation with electromagnetic sweeping, these specialized scanners capture images in an astonishing 50 to 250 milliseconds. The high-fidelity imaging that drives modern medicine is a direct result of this engineering evolution. It requires precisely shaping the photon beam with static filters, while simultaneously pushing the mechanical limits of continuous rotation hardware.